Hello, I am Shivani. Welcome to this video on Grover's algorithm. Grover's algorithm once again demonstrated the power of quantum computer in that the algorithm significantly reduces the number of operations that we need to solve the problem as compared to the classical computer. And this algorithm is also one of the important algorithm which shows the how quantum computer overpower the classical computer. As we are entering the stage of big data, searching through the enormous data sets efficiently is of the highest priority for many major companies. So Grover algorithm has the potential to speed up the data searches. Love Grover has invented the algorithm in 1996. Just like Deutsch's algorithm, it also speeds up over the classical algorithm in terms of query complexity. Of course, to implement this algorithm for real world data searches, we don't have oracles that can answer our questions. We need to construct an algorithm that does the work of the oracle. Let's discuss it with an example. Suppose we have four cards in front of us and they all are facing down. We know that one of them is the ace of hearts. So this is the card that we want to find. So how many card may we must turn over until we know the exact location of the ace of hearts. We might be lucky or turn it over the first try, or might be unlucky and turn over the three cards, none of which is the ace of hearts. So if we are unlucky and haven't turned it over after three tries, then you know the last card must be the ace. So we know where the ace is after turning over between 1 and 3 cards. So on an average, we have to turn over 2.25 cards. And this is the problem. This problem is the one that Grover's algorithm tackles. So let me rephrase the problem. Suppose we have four binary strings 0, 0, 0, 1, 1, 0, and 1, 1. We have a function f that sends three of these strings to 0 and other one to the 1. And we have to find the binary string that is sent to 1. For example, we might have function 0, 0 value is equals to 0, function 0, 1 is equals to 0, function 1, 0 is equals to 0, and function 1, 1 is equals to 1. The problem now asked is how many function evaluation do we need to make before we find function 1, 1 is equals to 1, which is our winning function. So we are just restating the problem, wording in terms of functions instead of cards. So with all query complexity algorithm, we construct an oracle or a black box or gate that encapsulates the function. On an average, this will take n by 2 trials and in terms of computational complexity. So for classical computer, the complexity will be the order of n, but in the Grover's algorithm or in the quantum computer, the complexity it states the order of root n query. So the algorithm has basically two steps. The first step is to flip the sign of the probability amplitude connected to the location that we are trying to find, and second is to amplify the probability amplitude. This is the kind of circuit diagram for the Grover's algorithm. This algorithm has three different steps. The first step is putting all the qubits through the Hadamard to put them in superposition states. And second step is putting it through the oracle function. And what ends up happening is we can see from here it is similar to Roche's algorithm. I'll discuss each steps. And the third is the putting Hadamard again after putting it into the oracle function, and which applying the state change to the qubits, and which once again reflects the input, and that's what we are looking for. Okay, let's get into its QISKIT implementation. But what is Oracle actually doing? Oracle, it's given a function that if the input is winner, so we can encode our input as the basis state. So remember, for the two qubits, we represent four input states 0, 0, 0, 1, 1, 1, and 1, 0. Let's suppose our winning state is 1, 1. So if we feed our winning state to the oracle, we get back is minus 1, 1, and this is the way oracle is gonna work. So we want a circuit that flips the sign of the 1, 1 state, that is the winning state, and for that we have a gate that is control Z or CZ gate. Let's get into its QISKIT implementation. So I have already created the notebook here. So from Qiskit, let me import everything. From Qiskit visualization, import histogram to see the graph, matplotlib, clear visualization of the diagrams. Okay, so let me define the oracle circuit. So the oracle circuit equals to the quantum circuit. This won't be our main circuit, okay? So I'm going to have the qubits again, but we don't have any classical bits over here. So I'm going to deal with the qubits for now, with the two qubits for now. I'm going to give it a name, oracle circuit, whatever you want. I'm giving it name oracle circuit, and only quantum bits, and naming it oracle circuit. Okay. Now there is a control Z gate that will flip the sign of the winning state. Okay, so I need to apply that, right. So I'm going to make the oracle to into its own gate. So for that, oracle circuit yeah. So let's see how it looks. Let me draw this. Yeah. Um, this is our CZ gate here. This is our CZ gate which act as the oracle. You can see here. Now I'm gonna define my Grover circuit. For that I'm going it name main circuit. So here I'll give two qubits and two classical registers. Then applying Hadamard, and this prepare my superposition state. And then I'm going to add on my oracle so that I can query each one of the state at the same time. So I'm using append over here and going to, so once again let's draw it to check how it looks. Okay, and Okay, okay. So yeah, we need this is the circuit diagram. We need one more thing to tie all these things together. With the oracle and the reflection operator, we can do something called amplitude magnification. So with amplitude magnification, we can amplify the probabilities of winning state. Let's see how it's work. There is geometrical interpretation. Okay, let me show you. So this is the kind of geometrical interpretation. So let's think about our winning state is W and our superposition state is S, and our winning state is represented as bracket W 0001, which is equals to 1 1, that is our winning state, and superposition state as cat s1, which is equal to 1 1 1 1 and half, that is the normalization normalized by half 1 by 2. So we can think about these two state as the vectors in space, and which is orthogonal or almost at the right angle, and we can come up with a new state within the span of W and S, within the span of W and S, yeah, and we can come up with a new state, and which is called W prime, which is called W prime. So it is defined as 1110 with a normalization factor 1 by root 3. And so now when we apply the oracle operator to S1, so S1 goes into the oracle, and oracle flip the sign of the winning state. So what comes out is this vector 1 1 1 minus 1 with the normalization factor 1 by 2. So our S1 has been reflected around W prime and got a new state, that is S2, मतलब like case S2, and this will reflect so our S1 has been reflected. So now when we apply reflection operator, and this will reflect our new vector state S2 here about our original S1 vector, and then we will ended up getting S3. We can see that combination of these two vector actually brings us the closer of our winning vector, that is W here, cat W here. So number of times we apply the amplitude amplification will scale as under root n. So let's see how it works in QISKIT. I'm going to write reflection circuit over here in the QISKIT. So here I'm going to write reflection circuit, and again I'm going to create this as a separate circuit and append, and then we'll append it to the main circuit. So let's do it. 2 qubits, and name it, going to name it reflection circuit, right? So we want to do is an operation that takes our superposition position state back to the zero state. So we can do, what we can do is that by applying the Hadamard on every qubit, and then apply a circuit that appends that applies a negative phase. So I am going to add Hadamard on all my qubits to bring them back to the original state, and then apply the Z gate on both of my qubits, and then CZ gate. So let's do it. right? And this is our circuit that will apply a negative phase only to this 0 0 state, and then I'll transform it back by applying the Hadamard on both the qubits and turn this to the gate. So next step is applying Hadamard again. Okay, then transfer it to the gate. Gate, sorry. And let me draw this. Apply all this thing, and let's draw it reflection dot draw. So the kind of circuit which we are getting is this is the kind of circuit which I am getting, and this is our circuit that will apply a negative phase only to the 0 0 state, and then I'll transform back it applying the Hadamard on the both the qubits, and in turn we get the gate. So this is the circuit diagram which ultimately I've got after applying the reflection operator. And let me append this reflection circuit to the main circuit. So yeah, main circuit dot append the reflection circuit. Then I'm going to measure it. Right, and let me draw it again. Oh, spelling mistake here. Oh, I might have run it twice. Wait. So yeah, this is the kind of circuit which was running in our head, applying the Hadamard on both the qubits, then passing it to the Oracle circuit, and then applying the reflection operator, and ultimately measure the states. So let me run it on Cosm simulator. For that, backend dot get backend. Here I have wrote backend is equals to a dot backend. You can write anything like simulator is equals to a dot backend, whatever you want. Won't make any changes over here. Executing the result. Main circuit as backend is backend, number of shots, and storing the result in the function result. Okay, let me call the counts. Plot histogram. So yeah, we have got one out of it, and which is the we have got one out of it, and which is the winning state. So we have implemented Grover's algorithm, and we only used one call to the oracle in order to find the winning state. So this is how Grover's algorithm actually works, and and we have seen how we have implemented in Qiskit. Its implementation in Qiskit. So this is all about Grover's algorithm. Is clear. Thank you.